Hello, everyone. My name is Yixiao Du. I'm a first-year PhD student from Cornell University. Today, I'm going to talk about sparse linear algebra and HBM-Equipped FPGAs. This work is done in collaboration with Yuwei, Zhongchun, Zhou, and Professor Zhiru, Zhang. So, sparse linear algebra has a very broad range of applications. We can use it to solve a linear system of equations. It can also be used in compressed neural networks where the weight matrix is pruned to be a sparse matrix. It also plays a role in graph traversals such as breadth-first search. Here, the adjacency matrix of the graph is a sparse matrix. Before talking about the acceleration of sparse linear algebra, I would first like to introduce the characteristic of this workload. So this is an example of a sparse matrix times a dense vector, and I listed out the compute pattern of generating the first 5 elements in the result vector. So this compute pattern exhibits a low compute memory access ratio. So if we look at every line in the list, we only have 2 operations there, but we need to do 4 memory accesses. This is because the elements in matrix A is used only once. This low compute memory access ratio leads to a situation called bandwidth bound, which refers to the performance of the sparse linear algebra accelerator is determined by the memory bandwidth. And if we also look at the access pattern to the vector B, the pattern is completely random because the non-zero distribution in the matrix A is random. And finally, we also have carry dependencies that because the matrix vector multiplication naturally incurs accumulation. And that dependency must be especially taken care of when designing any kind of sparse linear algebra accelerators. So based on these characteristics, we summarize the challenges to the acceleration of sparse linear algebra into 3 aspects. So first is the bandwidth bound problem. The second is how we handle the random access. And final one is we need to take care of the carry dependencies. So we propose high sparse as our solution to these challenges. So high sparse is a high performance accelerator of sparse matrix vector multiplication. And the key ideas of high sparse is to co-design the sparse matrix format and the accelerator architecture to better utilize memory bandwidth. And also, we implement dynamically executing pipelines to handle the random access and carry dependencies. So there are a lot of previous attempts of accelerating sparse linear algebra on FPGAs with DDR memory. However, high bandwidth memory, or HBM in short, provides exceptional bandwidth when compared to the DDR platforms, so which gives us the potential to have higher performance than previous work. However, that high bandwidth of HBM relies on concurrent access to multiple HBM channels, which means when designing the accelerator architecture and the sparse matrix format, we must avoid any kind of channel conflicts. So now speaking of the matrix format, let's take a look at a very popular sparse matrix format called compressed sparse rows, or CSR in short. Unfortunately, this format is not good at utilizing memory bandwidth. It has 2 problems. The first one is non-streaming access caused by its indirect addressing and contiguous storage of rows. So in this example, we have a 4x4 matrix and its corresponding CSR representation in memory. Suppose we exploit the parallelism across the rows of the matrix and have 2 process engines in the system to process the matrix in parallel. To begin with, the 2 PEs has to access the row pointer array to look up the start location of the first and the second row of the matrix. So they have to jump to that start location after accessing the row pointer. So this memory location jump breaks the streaming access. And also when accessing the first and second rows, you can see by the coloring, the access is still not in streaming mode. That is because the PEs are designed to access different rows from the matrix, while the rows of the matrix are stored in contiguous memory locations. So after reading these rows, they have to jump back to the row pointer, which again shows the indirect addressing and the broken streaming access, and to jump back to access the normal non-zero data. The other shortcoming of compressed CSR format is it cannot avoid channel conflicts when it is stored on HBM. That is also because the contiguous storage of rows. So suppose we assign the first two rows to HBM channel 1 and the second two rows to HBM channel 2. So still from the coloring, we can easily find that the two PEs has to access the same HBM channel at the same time, which causes channel conflicts and decreases bandwidth utilization. So in our custom matrix format, we use row switch markers and we cyclically store the rows to different HBM channels. So this ensures full streaming access and also resolves the channel conflicts when accessed by multiple PEs. So still with the same example, you can see the storage of rows into the HBM channels has been changed, and the two PEs can now access different channels at the same time without any conflicts. While after a PE accesses its first row, it will stream in the next element, which is the next row marker, to tell the PE to switch to the next row. By introducing the next row marker, we get rid of the indirect addressing caused by the row pointer array, so therefore the PE can keep streaming in all the data. While in real world, one access to the HBM channel not only deliver one element, but it delivers you multiple matrix elements at the same time. So therefore, according to the number of elements delivered per memory access, we pack multiple PEs to form a cluster. So in this example, we pack 4 PEs into 2 clusters with 2 PEs per cluster. So when applying this vectorization at each cluster's point of view, the access is still streaming without any HBM channel conflict. So now let's come to the other side of the co-designing, which is the architecture of the accelerator. In high sparse, we have 16 channel cluster pairs, and inside each cluster, we have 8 PEs. So the number 8 comes from the HBM word length divided by the matrix element bit width. So now let's come to handle the random access to the vector. One straightforward way is to duplicate the input vector to every PE in the system. This is simple and the PEs can access the vector without any conflict. However, this approach has a very high demand for on-chip memory. Another approach is to share the vector across a group of PEs. So this approach remains a very efficient use of on-chip memory. However, we need to deal with span conflicts. So high sparse takes the second approach because we have 128 PEs in total in the system, so that will be too much to duplicate the vector. So inside the cluster, we have 2 shuffle units, which is highlighted in the red boxes in the figure to resolve the bunch conflicts. And we also have a set of vector buffer access unit called VAUs to process the read requests to the vector buffer banks. So inside this cluster, as you can read in the figure, we also have a matrix loader to load the sparse matrix, and we also have a set of PEs to do the computation. And the packed and unpacked units are required since we also pack the we also do vectorized access for the vector and the results to better utilize the HBM bandwidth. So as for implementing the shuffle unit in HLS, it is not an easy task. So here is an example of a naive shuffle unit written in HLS. So when this design is pushed through the HLS flow, the tool will assume the worst case traffic pattern and process all the input lanes sequentially. This is because there's no arbitration logic written in the HLS code. So as a result, if we have n input lanes, the pipeline II of the shuffle unit will be n. So we will have a very poor performance. So our solution is to implement an explicit arbitration logic and a dynamic reset mechanism to resolve the bunch conflicts. So here is our design, and let me walk you through it. So in the shuffle unit, first things first, we need a crossbar to route the memory requests, and then we need an arbiter to do arbitration across the input payloads and control the crossbar. If a payload is not granted for access, we send it back to the input of the arbiter so that it will be arbitrated again. And our arbiter operates in a round-robin manner, therefore no input lane will be starving at a very long time. And finally, we have these dependency programas to implement these feedback paths to sending back their payloads. So in this way, with this subunit, the bind conflict is resolved in a dynamic way. So we also need to tackle the current dependency problem, remember? So here's another example of how to write the process engine in SVM-V. And when this design is pushed through the HLS flow, the HLS will increase the pipeline II to pull apart the carrier dependencies. And a typical way to solve this dependency is to implement data forwarding. So it's pretty common in RTL design, but it's hard to do so in HLS because the pipeline registers are not visible in the HLS code. This is one main reason that driving people back to develop this accelerator in HLS, but in RTL, sorry. Our solution is to implement data forwarding based on the data structure called in-flight write queue. So in-flight write queue consists of a set of shipped registers that keeps the past information from writes, from past issued writes. So here's a code snippet of how we update the in-flight write queue. So you can see it is shifted every iteration, or if the I is 1, then it's shifted every cycle. So this in-flight write queue actually have the same functionality as the pipeline registers, and it stores the data just required to detect the dependency and forward the correct value to the input of the adder. So when we implement high sparse on the multi-die FPGA, we actually came across another challenge. So let me show you with this example. So if we simply wrap everything inside one kernel, when implemented, the frequency is only 117 megahertz because of many die crossings that is not pipelined. So each combinational die crossing causes of 2 nanoseconds delay. So that's the problem of time enclosure. And you may ask, why don't we pipeline these die crossings? Well, it is hard or nearly impossible to do so because we wrap everything inside one kernel, so there's no floor planning, and we cannot predict which signals will cross the die boundary. So we don't know which signals to pipeline. So our solution is to divide the design into multiple kernels and place each kernel within one chip die. So in this way, because we divide up the design pre-hand, we know which signals will cross the chip die, and also the division helps us to confine the logic within the same die. So therefore, we can easily identify the cross-die signals and add relay modules and registers to pipeline it. After this optimization, our design runs at 237 megahertz. So we implemented our design on the Xilinx Alveo U280 FPGA using 16 HBM channels to store sparse matrix, 2 HBM channels for the input and output vector. So these 18 channels gives a total bandwidth of 258 gigabytes per second. As for the buffer, we implement a 4 megabyte output buffer and a 128 kilobyte backup buffer on chip. And we also implement 8 process engines for each HBM channel. So therefore, we have 128 process engines in total. Our design is completely written in HLS and runs at a frequency of 237 megahertz. So this table shows the resource utilization of high sparse on Xilinx Alveo U280 FPGA. As for evaluating our design, we run high sparse on various data sets. These data sets come from compressed weight matrices of the transformer model and also some adjacency matrices from different graphs. We compare our design with the CPU baseline, which is the Intel MKL library running with 32 threads on a Xeon Gold machine, and also the GPU baseline, which is the NVIDIA Sparse library running on the GTX 1080 Ti graphics card. So this table shows the throughput numbers of MKL, Sparse, and high sparse. So in general, high sparse is 4.1x faster than MKL, and the throughput is almost the same as sparse. As for the bandwidth efficiency, our design is 4.6x more bandwidth efficient than MKL, and also almost 2 times higher bandwidth efficiency when compared to sparse. As for the energy aspects, our design is 37x more energy efficient than MKL and 3.7x more energy efficient than sparse. So we also compare our design to previous work on FPGAs, which are Thunder GP implemented on a DDR FPGA, and the Vitis Sparse library implemented on the same platform as HiSparse. So when compared to 300GP, HiSparse is 2.2x faster, and when compared to Vitis Sparse library, HiSparse is 1.4x faster than Vitis Sparse library, using the similar amount of memory bandwidth. In conclusion, HiSparse makes these following contributions. So we identify the challenges of accelerating sparse linear algebra on FPGAs with HBM, and we present techniques to tackle these challenges using SPMV as a case study. And we also illustrate the best practices in HLS to dynamically resolve bank conflicts and carrier dependencies. Finally, our design is open source and it's available on GitHub. As for the future works, we can apply the same techniques to the acceleration of other sparse linear algebra operators, and we can also try to enhance the HLS tools to automatically solve bank conflicts and carrier dependencies. So that is all of my presentation today. Thank you for your time.